let's get started. So I'm hoping that you'll have your grades by the end of today or sometime tomorrow. But in the meantime, we're going to move on. So I'll ask you please not to have your computers open in class. Thanks. And we're getting on to talking about matrices and vectors. And for those of you who like to be entertained, the Khan Academy has a series of videos on matrices and vectors. So you can find material in our textbook, or you can go through and watch these videos, and it'll give you the basics of matrix dimensions, representing relationships with matrices, scalar multiplication, matrix multiplication, how to add and subtract matrices. And then later on, there'll be some sections on finding the determinant of the matrix, and we're even going to get to eigenvalues and eigenvectors. So if you really want to brush up on your matrices, then this is one place to get it. But in the textbook, you'll find a section on matrices in Chapter 8. I think it's Section 2. And for those of you who want to practice examples, there are examples there for you to practice on, and with the odd numbered answers in the back of the book. Eric, I didn't see at the back there. Do you know when the grading is going to be finished? Okay. Okay, so again, the Khan Academy is a great place to go if you think that you learn better while being entertained. Okay, so now we're going to come to the idea of defining what's called a vector, and this leads on to matrices and matrix multiplication. Now, if you're in the plane, so we're going to be talking mainly in 2 dimensions, but everything we say here extends in a visual way that you can imagine to 3 dimensions, and in non-visual ways to higher dimensions, so that everything we talk about can be generalized to any number of dimensions you want, with all the formulae that we get together and the methodologies that we propose, just simply applying in higher dimensions, and I'll talk about that as we go along. But to begin with, we'll just talk about the basic notion of a vector. So, whereas a scalar is an object that has a single value, a vector is an object that has more than one value. And usually it has a list of values, and those values are called elements. Now, when you worked in the Cartesian plane, 2-dimensional plane, and by convention, we can make it infinite in both directions, and we have a point x and y. Now, when we write a point x, y in the plane like this, let's see if this is any better. No. We're writing it as an ordered pair. Now, when I say ordered pair, the order is important because the x is always listed first and the y is always listed second. So this is a convention. There's an ordering. There are alternative coordinate systems. Do you know of any other alternative coordinate systems that you worked with for looking at points in the Euclidean plane instead of x and y? Spherical. Okay, so spherical, you would have something called r and an angle theta. Now, x and y can be related to r and theta using trigonometry. So what is x equal to in terms of r and theta? R cosine theta and so on. I'm going to have to use my own. Okay. Now, in vectors, what's important is very often understanding what the magnitude of the vector is. So the magnitude is the length r, and then its orientation in space is given by the angle theta. We're not going to be working in r and theta at all. We're going to be working in the Cartesian coordinates x and y. Now, when you add 2 vectors together, you'll say, okay, I've got a vector over here, this is a point which you might call AB, and this is another point which you might call CD. Now, when we represent these as vectors, the standard notation is to write this as a column. So when we, in vector notation, rather than Cartesian coordinates in the plane, we would write this as AB. And in vector notation, we would write this as CD. Now, if I said to you, I'm going to define addition of 2 vectors, AB plus CD, as equal to A plus C, B plus D. So, in fact, I'm just defining addition here to be element-wise. Then what would this look like here? Okay. This distance here is A. This distance here is B. And I'm going to erase this now. And I'm going to add to B, I'm going to add A. So, and if this distance over here is B, sorry, this is CD. Okay. So that's A and C. And over here, I've got D and B. So if I'm going to add D to this, to B, then I'm going to get a point out there. So does everybody see how the addition works? So when you add 2 vectors together, you're adding the x components and the y components to give you a new point. This is A plus C and B plus D. Now, if you're good at geometry, what you can show is that if you take the vector AB and you add to it the vector CD, that will bring you there. Or if you take the vector CD and you add to it the vector AB, that will bring you there. So you can do it either way around, and the geometry works. And so that's the geometric interpretation of adding vectors. But in this class, we're not going to bother much with these geometric interpretations until we come to eigenvalues and we try to understand what those are. But this is just to give you some understanding of how you add vectors. Now, we can give vectors names. So we can call this a vector u and this a vector v. When we talk about vectors and we write them, sometimes we underline them or we put them in boldface. And this indicates to you that this is not a single-valued thing. This is a special object which has more than one value. And so this would be u plus v. And then, in order to work out what u plus v is, you have to look at its elements and add those together to get the sum. So that's just the geometrical interpretation. Are there any questions about vectors? Okay. So here's vector algebra. Again, it's, you can find it online anywhere at Wikipedia, Khan Academy, or you can look at your textbook. And there are two things that we need to define. One is, if we've got u and v made up of two elements each, and we add them, it's element-wise addition. But there's also something called scalar multiplication. So if we take a vector and we multiply it by 2, then we're going to get something that's twice as large in exactly the same direction. So scalar multiplication never changes the direction. Scalar multiplication multiplies each of the elements in the vector by the same constant, so it never changes direction. So that would be multiplication by 2, and then something like that would be multiplication by a half. So when you multiply a vector by a constant, and if you multiply the vector by -1, then you would just take all the positive values if it's positive and give it negative values. If the vector's in this quadrant over here, then it means its x value is negative and its y value is positive. And if you multiply by that -1, you come from the second quadrant to the fourth quadrant. So this is called reflecting around the origin. So multiplication of a vector serves to change its length. So if you multiply by a number greater than 1, you're expanding it. If you multiply by a number between 0 and 1, you're contracting it or compressing it. If you multiply by a negative number, you're reflecting it through the origin, and then if that negative number is less than -1, you're going to expand it in the opposite direction. And if it's between 0 and -1, you're going to contract it, but then in the opposite direction. So does everybody understand the effect of scalar multiplication on a vector? Okay. Now we come to matrix algebra. So a vector is an object that has, in this case, this is 2 rows, 1 column. If I went to 3 dimensions, and I said this was x, y, and the z-axis, then I could have some point in the space over here that I might call ABC, and then I have an arrow connecting up there. Then my vector is ABC, like that, and this would be 3 rows, 1 column. And sometimes it's just 3 by 1. So a vector is this object. It always has 1 column and a certain number of rows that tell you of its dimension. So this is 3-dimensional vector. So vectors are special names for objects that have 1 dimension that is greater than 1 and the other dimension that's equal to 1. Okay? Now we can generalize this to writing down objects that have more than 1 dimension in both the rows and the columns. The simplest of these being something that is a 2 by 2 object. And whenever there's more than 1 dimension in both the rows and the columns, we give it a more general name. We call it a matrix. So A, B, C, D is a 2 by 2 matrix. We could have a 2 by 3 matrix. So that would be 2 rows and 3 columns. A, B, C, D, E, F. Or we could have a 3 by 2 matrix, which would be A, B, C, D, E, F. Or we could have a 3 by 3 matrix. A, B, C, D, E, F, G, H, I, like that. So if you get more into mathematics and sometimes even into statistical models, you might work with matrices that are called n by m matrix, n rows, m columns. However, we are only interested in square matrices. Square matrices are n by n, so that's a number of rows equals number of columns. And we will not be dealing with arbitrary dimensions, which is n times m. We'll only be dealing with square matrices, and we'll be confining our attention generally to 2 by 2, and maybe we'll talk a little bit about 3 by 3 matrices. When we build our age-structure models, then we'll talk about an n by n matrix, but that matrix will have a very special structure, and we'll call it a Leslie matrix, because Leslie was a famous biomathematician from the 1940s and early 1950s who developed a lot of the theory associated with age-structure matrices. Okay. So, any questions? Now, addition is always fairly simple. You can only add matrices that have the same dimensions. So you can add a 3 by 2 matrix to a 3 by 2 matrix, or you can add a 2 by 2 to a 2 by 2. And the reason why they have the same dimension is that the elements have to line up, because addition, as we said, is always component-wise addition. So here's A, B, C, D, alpha. We've got 2 matrices there. Can we see them? Okay, A and B. Yeah. So A is A, B, C, D, and B is alpha, beta, gamma, delta. And when we add them, we add the components. Now, there's another way of working with notation in matrices and vectors. And the reason for this is that if you get to a 7 by 7 matrix, how many elements would a 7 by 7 matrix have? 49. So you'd be listing the whole alphabet and then the Greek alphabet, and then if the dimension was big enough, you'd run out of symbols. So we have a very simple way of enumerating matrices. So an n-dimensional vector. So how many rows would an n-dimensional vector have? N rows, one column. We would write as x1, x2, up to xn. Okay? And an n-squared matrix, which I might call A, I then might write this down as, so it's got n rows and n columns. The first element is the first element, little a, of the first row in the first column. The second element in the first row would be the first row in second column, the first row in third column, up to the first row in nth column. How many of you have never seen this notation before? Okay. Then we're now in the second row, first column. Second row, second column. Second row, third column. Second row, nth column. So somewhere we would have aij. This would be aij is equal to element in ith row, jth column. Okay? This notation is very convenient, and we will use it sometimes, but mostly we won't. Mostly we'll be dealing with specific numbers. And then you'll finally get an1, nth row, first column, up to ann, nth row, nth column. And if you have a look, all these, like a11, a22, a33, a44, up to ann, that's called the diagonal of the matrix. So only square matrices have diagonals. And to understand matrices, you really have to understand square matrices, and then matrices that aren't square, where they have n rows and n columns, are an elaboration that is useful in some more advanced areas of mathematics and statistics, but generally, predominantly, people are interested only in square matrices for most things. Okay. So now, the other thing that I should finally say is that there's something called the transpose. The transpose of a vector, or the transpose of a matrix. A transpose is where you rotate it so that all your rows become columns and all your columns become rows. So the transpose of this vector is sometimes written as, if this is x, and I underline it, then the transpose is either written as x transpose, or sometimes it's written as x prime. The problem with writing it as x prime is that sometimes we use a notation prime for derivatives, and sometimes we use it for transpose. Usually, it's not a problem because it's clear we're not dealing with calculus. And the transpose means that you write this as a row, x1, x2, up to xn, like that. And the transpose becomes important when considering multiplication. So multiplication is perhaps the most difficult thing to master about the very basics of manipulating matrices before you get into finding certain properties of matrices, but just doing basic arithmetic. Multiplication may seem a little twisted at first, but after working with matrices, you'll see that why it has to be defined like that, and it's really quite simple. So if I've got two vectors, x equal to x1, x2, and x3, and y equal to y1, y2, y3, then I can define x times y, and this is in the sense of vector multiplication. So that is vector multiplication. What you have to do is you have to basically say, I write x as its transpose. And I multiply this by this, I multiply that by that, and I multiply this by this to get x1, y1, x2, y2, x3, y3. So if I define vector multiplication in this way, this is what it means. It means you multiply rows by columns. You always multiply rows by columns. But now what we're going to do is we're not really interested in that so much as a vector multiplying a matrix. This, for those of you who know a little bit more and take physics, this is what's called the inner product of two vectors. But the most important thing is multiplication of a matrix by a vector and a matrix by a matrix. So let's say a matrix A times a vector x, which I'll write like that. And in two dimensions, if this is a 2 by 2 matrix, and this is a 2 by 1 vector,